Alright, the next thing we're going to talk about is using this concept of solubility in a type of reaction called a double displacement reaction. Now we talked about single displacements, so what's double displacement? Double displacement is a reaction between two compounds and it'll create two new compounds. So the format for double displacement says AB plus CD will make CB plus AD. So you can see what happened here. A and C switched places. A was bonded to B, now A is bonded to D. C was bonded to D, now C is bonded to B. Now here's the important thing. For the first type of double displacement reaction. One of these new things must be a precipitate, which means that we're going to have to check the solubility of the products that are made. Using our solubility table, we're going to have to clearly identify which compound is the precipitate. If we find out that they're both soluble, that means that there is no reaction. Now let me show you why that is. Okay, I'm a pretty visual person. Now here's one important thing for you to know. For a double displacement reaction, AB and CD have to be soluble. They have to both be dissolved in water in order for the switching to occur. So when I put AB in water, I'm going to get some A plus, whatever A is, and I'm going to get some B minus. Right. In my other container, I'm going to have some C plus and I'm going to have some D minus. That's what we mean when we talk about things that dissolve in water. It means that when we put those little solid crystals in there and we stir them all up and we say, ooh, they disappeared, what really happens is that they broke into little tiny pieces. They broke into the positive and negative ions. The positive and negative ions are still now free to float around and come into contact with each other, but they don't stay in contact with each other very long. Now, in a double displacement reaction, we obviously are going to put both of them together in one beaker. Okay, so let's say that CB is our precipitate. CB is the precipitate. That means that when C and B, when they're mixed together, when C and B get together and make a compound, they don't come back apart again. So that means that what I'm going to get is a precipitate. They're going to stick together and they're going to stay together and they're going to create a solid. They don't dissolve in water, so they stay in their solid form. So that means that they're going to sit on the bottom of the beaker. Well, what happens to A and D? If A and D are soluble, that means if that compound's soluble, It means even though A and D still run into each other, they don't stay together. The water pulls them back apart again. This is really what a double displacement reaction is. We're going to see this in a lab a little bit later. We're going to look for formation of precipitates. Okay, so this is what a double displacement reaction looks like. Let's get some actual examples of actual equations for double displacement reactions. Okay, now these are kind of challenging. You have to have your whole brain focused and working. Okay, so when you run across these double displacement reactions, this is what you're going to see. You're going to see a compound mixed with another compound. Now you kind of have to ask yourself, okay, this one's A, remember, so A is the sodium. This is A, B, C, D. Remember this C. A and C are going to switch places. So on the right side of the arrow, I'm going to have aluminum and OH. Okay, and I'm going to have sodium and NO3. Now, please note that I didn't put a 3. I didn't put this in parentheses, because before I do that, since they're switching partners, you might have things with the charge ratios might be different. So you have to check the oxidation numbers before you write your final formula. Okay, aluminum is +3, and hydroxide, which is on the back of your table, is -1. Sodium is +1, and nitrate on the back of your table is -1. So I look and I say, aha, so when sodium and nitrate bond, they bond 1-to-1 ratio. Aluminum and nitrate bond in a 1-to-3 ratio because aluminum is +3. So the hydroxide, when aluminum and hydroxide get together, they're going to need a 3. Remember, these are unbalanced equations. You know, we could balance them and then we'd have the same number of NO3s and OHs on each side. Okay, now the next thing is I have to go to the solubility table and I have to check to see which one of these is the precipitate, which one of these is not soluble. Okay, so when I go there, I'm going to look, first of all, I'm going to go back to the solubility table and I'm going to look up aluminum or hydroxide in the rules. So let's jump back there. Okay. So I'm going there, aluminum or hydroxide. Hydroxide is down here. It's the last one. It says it doesn't dissolve. Is aluminum an exception? Aluminum is not an alkali metal, so aluminum hydroxide does not dissolve. That means that aluminum hydroxide is a precipitate. Okay, so let's go back to our original table here, and how am I going to show that? I'm going to draw a downward pointing arrow underneath the aluminum hydroxide formula. This means precipitate. Okay, then the nice thing about double displacement reactions is that only one of your products is going to be precipitate. You're never going to see a reaction where you have double precipitates. You might see no precipitate at all. That's a no reaction problem. Okay, once you've identified the precipitate, this one is automatically soluble. You don't have to work anymore. Okay, let's look at another example here. Okay, so here we have potassium sulfate and silver nitrate. Okay, so I say, alright, this one's A, this is C. A and C switch places. Okay, so instead of potassium and sulfate, I'm going to write silver and sulfate. Instead of silver nitrate, it's going to be potassium and nitrate. Okay, I'm going to change. I look here, I see silver nitrate is -1. And silver, there's one silver, so I know silver has to be +1. You got to do a little bit of detective work here. Look at the back of my table, sulfate's -2. K is always +1, nitrate's always -1. So all I have to do is put a 2 here. Okay, now let's do this one first. It doesn't really matter which one you start with. If you find one that's soluble, the other one has to be precipitate and vice versa. Okay, so I'm going to go to the periodic table, look for something about a rule about silver or a rule about sulfate. Back to the solubility table we go. Here's sulfate. It says most of them are soluble. So now I say, okay, is silver an exception to the rule? Look over here. Yes. Silver and sulfate together are an exception, which means that silver and sulfate are the opposite of the rule. They do not dissolve. So that means that I have identified that silver sulfate is the precipitate. So I just put a downward pointing arrow. So that's how you do double displacement reactions. Okay, the last thing that we're going to talk about in this one, right, is a special group of double displacement reactions that are called acid-base neutralization. And this is a special double displacement. Okay, it's always an acid plus a base. Well, what's a base? You should know what acids are by now. But bases are compounds that contain OH. They're special because they, instead of making a precipitate, they make water. And they also, the other product they make is an ionic compound. And these are usually soluble ionic compounds that are created. Alright, so let's look at the general form. General form is H, A. Okay, so this is the acid, and then whatever the acid is bonded to, plus B, OH. Okay, what happens is that the H and the B will still switch places. So you get HOH. This equals H2O. This is water. Plus whatever B is bonded to A. That's your ionic compound, Ba. Okay, let's look at some actual examples here. Okay, so let's look at the double displacement neutralization reaction between sulfuric acid and barium hydroxide. This is the acid, this is the base. Okay, now remember we said that H is going to bond with OH. It's going to make the water. And then we got the sulfate left over and the barium left over. Remember when you do this that the metal, the positive ion, is always first. If you tell me the compound's called SO4Ba, that's wrong. So the compound is BaSO4. Let's double check our oxidation numbers to make sure we write the formula correctly. Ba is +2. The back of the table, oh, excuse me, that's incorrect. Sulfate is -2, such as BaSO4. Okay. One more example. Okay, this is hydroiodic acid and potassium hydroxide. Okay, remember the H for the acid and the OH for the base always get together and make HOH, which is the same as H2O. And what's left over is the I and the K. K is the metal, so you have to write the K first. Don't write IK, that's wrong. K is +1. I is -1, so it's just Ki. Okay, and that's how you do double displacement acid-base reactions, which are also sometimes called water former. So if you see the word water former, you know that it's an acid-base reaction. They're called that because one of the products is always water.